Good day, everyone, and welcome. I'm Jack Van Horn from the University of Virginia, and I'm very proud to welcome you to this first edition of our 2023-2024 Foundations of Biomedical Data Science Seminar Series. This lecture series is supported by UVA's Integrated Translational Health Institute of Virginia, the UVA College of Arts and Sciences, the UVA School of Data Science, and through a grant from the National Institutes of General Medical Sciences. Since 2016, the Foundations of Biomedical Data Science Seminar Series is focused on the use of data science methodologies, artificial intelligence, deep learning, and statistical modeling as they pertain to differing themes in biomedicine and the health sciences. This year's theme is building partnerships for generative AI training in biomedical and clinical research, where we will enjoy presentations on Fridays from leading thinkers about the issues, the promise, the opportunities, and hurdles associated with the emerging methods in AI-based technologies applied to biomedical science data types, and the efforts by faculty educators in training the next generation of biomedical researchers to properly use those computational tools. Indeed, today, we are excited to announce that we are opening our 2023-2024 application cycle, encouraging junior faculty members working in the area such as the development of generative AI-based methods applied to biomedical research, and those junior faculty actively utilizing AI in their biomedical teaching to consider applying. We believe this will be an exciting and engaging program, bringing together AI platform developers and university educators to better understand the power, the promise, and the potential perils associated with the generative AI explosion. Participants selected for our Biomedical Data Science Innovation Lab program will leverage these seminar presentations as vital material for our culminating in-person manuscript and grant generation project to be held at the Bahia Beachfront Resort located in sunny San Diego, California in June of 2024, my apologies. Today, I am delighted to welcome our speaker, Dr. Brian Wright from the UVA School of Data Science. Dr. Wright is a 2024 BDSIL Mentor, and he is an associate professor and director of undergraduate programs at the UVA School of Data Science. Prior to this appointment, Dr. Wright was the director of George Washington University's graduate data science programs and served as a faculty member teaching machine learning, Introduction to Data Science, and Capstone courses on an annual basis. He also helped to co-found George Washington University's Data Science Institute. And prior to joining George Washington, Dr. Wright organized and led interdisciplinary teams of researchers at the University of Texas at Knoxville. He is the founder of DS Labs LLC and a data science consultancy that focuses on educational program development, algorithm construction, and data science-focused research and development efforts. His research sits at the center of education and data science, and he holds degrees in economics, public health administration, and higher education. He is currently working to develop predictive algorithms to increase Algebra 1 success in K-12 settings. In initiating the 2023-2024 Biomedical Data Science Seminar Series theme, Brian's lecture today is entitled Generative AI in Context. Professor Wright will talk about the road that led to the incredible explosion of generative AI that we are currently experiencing and that has rapidly emerged over the past couple of years, creating new research communities around developing adversarial neural networks and large language models, the results from which have recently proven disruptive across public, scientific, and educational spectra. In particular, he'll talk about high-level architectures that allow for large language models to be so effective and conclude with implications for research moving forward. As always, we are streaming this lecture live and for recording via YouTube. If you are watching on YouTube, thank you so much for joining us. Also, our specially selected 2023-2024 Biomedical Data Science Innovation Lab participants and alumni are encouraged to submit any questions via the chat feature in their YouTube sessions. I will be synthesizing these questions and will ask them on your behalf during the last 10 minutes or so of the lecture. And with that, welcome, Brian. Thank you so much for kicking us off this year. We really look forward to your lecture.
Thanks for that generous introduction, Jack, and I'm happy to be here. And let's go ahead and jump right in. I got one quick change for the introduction. You said University of Texas. That's University of Tennessee.
I beg your pardon, Tennessee.
No. My fellow colleagues from there would be remiss if I didn't jump in. But anyway, thanks again, Jack. This is great. So I'm just going to go over this kind of agenda here real quick. I'm going to lay out a little bit of data science concepts. I got a little bit of a poll, I think, for the audience too, because I'm not totally sure kind of the level of expertise I'm dealing with here. So I can adjust the talk a little bit based off those responses. But the meat of it here is kind of oriented around how did we get here? So I'll talk about the evolution of the field, a little bit of history, but we'll get through it real quick, and then we'll talk specifically about kind of large language models and the current, generative AI boom that we have. And to Jack's point, kind of end with some concerns. So here I have a quick poll. You can hit the QR code up there. You can think of this as like a scale from top to bottom, what is your experience in terms of relative knowledge of data science? If you feel like you embody data science wholly, you can hit that first one. But if you're not sure about the field, you're just getting started, maybe you're all the way down there on the bottom. And that'll just help me kind of context the talk in general. So there we go. All right, we do have one person that is embodying data science. That's good to know. Okay, very good. I'll give it a few minutes. There's probably a bit of a lag, and we're not totally sure how many people we have on the other end, but we'll go from what responses we get. There we go. Okay, we've got a couple more people. I've been using ML for many years. All right, very good. All right. Been planning to use it for many years. All right, very good. Give it a few more moments here. See if we get some more responses. All right, well, let's go ahead and move on. It might be that we get a few more people that jump on that poll kind of as we move throughout, but that's no problem. So it looks like it's kind of a split, right? So all right, we got one more. All right, so we got a little bit of this data science thing you say. All right. So I'll probably jump through maybe some of the front end ones, but kind of stick to the original plan here. So let's give just a quick overview of some of these data science concepts. So in particular, here at UVA, we have kind of this paradigm that we have embodied about what the way we think of the field of data science, and it's composed of these 4 components. I'm not going to get into this. There's a whole dissertation associated with this, but in large part, what we're talking about, large language models, generative AI, it's in this analytics category. Value, you can think of ethics, systems, you can think of cloud computing, design, you can think of data visualizations or human-centered design. So that's the way that we think about it. In the school, we have curriculum kind of designed around that, but in this particular talk, especially as it relates to AI, we're focusing on that analytics piece. And again, based off those responses, I think a lot of people are familiar with this, but I like to break down analytics just to think of it not just as machine learning, but there's also these components of applied mathematics, all right, statistical concepts, and then AI. All right, so AI is the big 10. I think that's going to spin. And so when we think about that, all right, again, just given the diversity of the audience, all right, artificial intelligence is the big sector. All right, machine learning is a subset of artificial intelligence. Artificial intelligence can be everything from just simple software engineering that helps computers think like humans. All right, that might be coding certain, as an example, coding certain interfaces between various medications to make sure that there's not any type of conflict to prescribe those to individual patients. That doesn't require any type of fancy machine learning. That's just simple software. All right, but that helps in decision making. All right, machine learning, when we go down inside the AI spectrum, we think of that as kind of more like probabilistic learning, like what are, kind of learning without being specifically coded. And then deep learning, which is where kind of the big boom associated with AI and generative AI in particular is really the focus of this particular year for this program, and then also kind of the focus of the talk. So it just helps contextualize that for everybody. And it sounds like, a good amount of people on the talk know this, but the context with which we're talking about this deep learning is actually kind of a very small portion. It is the one that gets the most attention by far, but it is a smaller portion of a larger big AI tent. All right. I just went through these, so I don't have to dig too much more into that, but these are kind of general examples of like classical AI, machine learning, that might be just product recommendations. And then deep learning is really the kind of the large language models or neural network applications in particular. All right. Okay. So this is important context too, as we go further down, right? In terms of like the level of AI, you just have more predictive power, but they're less explainable. So explainable should be on the bottom bar there. And we're going to spend most of our time up in the top. This is just a look again across the landscape of machine learning. And you can see kind of in the bottom there that neural networks, all right, is kind of a subset of the larger world of machine learning. And this chart's a little old. It probably should be updated, in particular to add some of the new methods that are starting to come out. Okay, so important part here to keep in context when we think of machine learning as really kind of a general purpose technology. That means it can apply it across all sorts of different market sectors, whether you want to elevate it to the level of electricity and the internet, maybe not, but anyway, that's the way that we think of it. So again, in good context, and part of the reason that we're here is to learn about how we can apply it in particular to biomedical situations. All right, I'm going to skip over that. All right, and these are just kind of contemporary points. All right, so what we've seen, especially over, since 2010, there was this big kind of milestone there associated with the error rate of classification and ImageNet. It went way down, at less than 5%. And the important part behind that is that's because that's lower than the human error rate. All right, so what we know is that humans were to look at this, there's about a 5% error. So it got below kind of the human error rate. And that started happening around 2010. One of these first big deep learning systems was Deep Blue. That was purchased. It was a European company that ended up getting purchased by Google. It's kind of the cornerstone of their AI-driven efforts internally. And then, as we move along, what we found, and this is just recently, there's been another, that same product, right? That Deep Blue kind of deep level architecture was used in another game for Go that is much more complicated than chess, right? And then that AlphaGo was the product that was generated there. But just recently, a simple trick by an amateur was able to beat the computer, I think 18 out of 19 times, right? Happened sometime in the last 6 months. And so no matter how good, I think anyway, no matter how good these machines get, and they're improving just at an incredible scale, all right, there still is some need for human expertise and experience along the way. So I think it's an important reminder as we go through all of this. We have really advanced, obviously, machine learning and generative AI product tools, but there's still kind of use cases and examples where if we just keep human in the loop, that they end up working better, or they can kind of beat them, even if the most advanced examples of that. All right. So again, this is just kind of context. These are things that our humans are good at, but this is things that machines are good at. And again, kind of interpreting and using the results, I think, is the key one with the check mark under the human there that we should keep in mind. All right, so I blew through that really quick. I always look for excuses to build in Back to the Future memes. So there's one here. So the question is, like, how did we get to this point? All right, so let's take a look at that. Oh, and this is much fuzzier than I thought it would be, but this is generally a timeline associated with the development of AI-based frameworks over time. And what we'll see, right, especially towards the end here, all right, it's kind of a rapid development in terms of the integration between machine learning developed kind of in the private sector and then in combination with what's going on in the academic, all right? So let me just jump ahead of this. And I think right here, right, the main takeaway from this, and again, this is what most people are kind of familiar with this, the nature of this, is that a lot of these artificial intelligence methods, at least the foundation of them, had been in development or at least being framed out in academic circles for decades, as far back as the 1960s, all right? But it really wasn't until the first part of the 2010s, right, when they started to get a ton of notice from the private sector about how powerful these tools could be as it relates to leveraging the business models that were occurring, especially in the kind of social media and internet search engine world. All right, and so right about this time, 2009, 2012, what we start to see is kind of this combination of all this long heritage of academic work. All right, starting to create really momentum inside the big tech firms of the day. And so a lot of people point to this kind of 2009, when Al Van Haren started to come out and talk about kind of, that this, Google's chief economist saying, hey, that this is going to be, statisticians are going to be in high demand. And then there's kind of this famous article in 2012 in the Harvard Business Review that called data scientists kind of the sexiest job in the 21st century. So all these years of progression, right, kind of led up to kind of this fluctuation point where popular kind of attention in the media and in the private sector really started to notice about how important these things were going to be. All right, and there's a bunch of reasons for this. This is just to take note of Hinton's influence in terms of this timeline. All right, the amount of contribution that he made throughout is not to be understated. And so we can take a look at this timeline, right, to put it in more context. If you haven't been to this before, this is an Ngram viewer from Google, and essentially tracks word usage over time in their digital libraries. All right, so here what we're searching for is artificial intelligence, data science, and machine learning. And maybe to nobody's surprise, right, and just to reinforce the ideals that we were talking about here, is that, there was this big bump, even back in the 1990s, right, and then again in kind of the early 2000s. But it went up and down, right? And so the question is, and people refer to these as kind of the AI winters, but I put some stars in here, and I'm going to try and contextualize, I think, why, and maybe it's obvious, but why exactly we saw kind of this recent takeoff, and then how all of this history kind of built up to this moment in 2015 that really catapulted us into this generative AI space. So let's talk about that in particular. All right, so here, right, early 2000s, I think, is a derivative of a little bit of an increase there. Is what we saw is the mass production of NVIDIA GPUs. That started to happen right at the beginning of the 2000s. And as we know, like a lot of these big data, and especially these deep architectures, really depend on, and now they've moved on, right, to new, more advanced kind of hardware. But that started to help us realize the power of these models that just wasn't available before. All right, so we had kind of a hardware contribution in the early 2000s, and we saw kind of a spike there right after that. All right, it's kind of a housing bubble. Everything went down after that. That's an excuse for maybe the kind of reduction that we saw. All right. So we had a lot of these mathematical software has been developed, or mathematical procedures that had been developed in academic circles for years. All right, but then we had this hardware contribution, and then we saw a software contribution that allowed us to link distributed networks together efficiently. All right, that hadn't been available really before. There would have been methods before, but Spark in particular allowed us to really combine this kind of computing architectures in combination with the hardware. All right, those two things together really kind of laying the foundation for what would be just a perfect development environment kind of leading into the 2015s. All right. And so here, I think, is really where we saw kind of this punctuated equilibrium. All right, so we had hardware that was in place that could support the computational needs that were necessary. All right, we saw some of this open source software that allowed those computers to be linked together in sophisticated ways that hadn't been available before. At least it became much more efficient. And then also, right around this time, like right around 2015, the accumulation of data starts to really take off. It had always been growing right through the early 2000s, especially with the creation of the internet. A lot of people point to the mass production of iPhones in the early 2010s as a real dramatic increase in the amount of available data. And so there's statistics here right in 2009 that 90% of the world's data had been created basically in the last 3 or 4 years. And you can see that with the explosion of internet-based companies, right, with the explosion of mobile hardware and cell phones. That was a huge point, right? So we had the hardware in place, we had kind of an ability to connect those together, and now what we've seen over that period right after that is this massive expansion in data, right? And so at that same time, Google, and they were kind of one of the first to field here, right? With their Deep Blue engine, they see these massive increases in the performance of their AI-based platforms, right? And so as a catalyst to that, and I think it's because of that, as I mentioned, kind of preceding this slide with about how things were folding out in the private sector in combination with the kind of contemporary media around AI and data science, you saw academic institutions starting to respond dramatically to the demand from the private sector to create degrees to support the expansion of this workforce. So at that same time, right, in 2012, leading up to 2015, we see a huge increase, especially in the graduate programs, masters in data science, masters in business analytics. It just went crazy. And in combination with that, the demand signal from the research community also increased dramatically as it, I think as a driving force for some of these big tech firms. They were doing their own internal research incubators, right? They're really trying to put a lot of PhDs, a lot of human capital into the development of these technologies because they started to see really crazy increases in the performance of their models right in that period of time. So to reinforce this ideal, I have here the same thing. If we add data set to that distribution that you just saw, it's the exact same as this. We just added the word data set. It just dwarfs the others there, right? So the expansion of data, if this is a measure of how often that is used in public discourse, which is supposed to be, we can see that this, the increase here just dwarfs the kind of the percentage increases we see in these other three areas. To reinforce the idea of the massive amount of increases of data that was occurring right at that same time. All right, so this is a chart from Michael Rappa. He was one of the first analytics programs, really kind of people, some say one of the first data science specific programs at NC State, and he's been tracking the increase in graduate programs over the last, 12 years. So here you can see, again, right around that 2014, 2015 timeframe, it's just an explosion in the number of programs from 2010, which might be less than 20, to 2015, where you're looking at 200 and then moving into 300 and then continuing to grow into the early 2020s. So that reinforces this idea, this second bullet here about this dramatic increase in the workforce that we saw. All right, this is a chart from Springer. They're tracking kind of big data publications that were occurring over time. And again, right here in that same sweet spot, 2010 to 2019, you just see this huge increase in the number of publications. From down there in the zeros to up to, pushing 8,000 in a period of 5 or 6 years. So again, it's this combination of investment from the private sector, attention from academia, and kind of leveraging these methods that have already been placed for a long time, the increases that we saw in the availability of data, and then the computing infrastructure, both in hardware and software, that were able to catalyst. It just created this perfect incubator for this explosion in methods, all right? And it's all kind of leading up to this AI revolution that we've seen over the last, 2 to 3 years. And so the question is, in leading into this kind of stark increase in artificial intelligence, what is that particular star? So let's get a little bit more detailed in the terms of what we're thinking about for generative AI in particular, and then actually specifically kind of large language models. Okay. All right. So a lot of the work here, I just wanted to give credence to Rafael Alvarado. He's put a lot of this together. He's an anthropologist, but specializes in kind of text analysis here in the School of Data Science. So let me borrow some of his slides for this, but they're perfectly germane for this talk, so I'm going to include them there. So thanks, Raf, for that. I appreciate it. All right, so let's talk about large language models in particular. Okay, so based off what we know, right? So more specifically, these large language models, what they're doing is they're really trying to predict the next token, all right, which is really just another word, right? So they're autoregressive, so they're very dependent on what happened right before that next prediction, but they can use billions of weights, all right, inside these deep neural networks, frameworks, okay? But it all boils down to basically trying to predict what the next word is. So, oh my God, the volcano is about to, right, erupt, all right? So in this example, I just want to lay that context, is that it can be distilled down just into that simple output. Obviously, the architectures that underneath these things are quite complicated, but the idea is just to predict kind of the next sequence of words. All right. Now, this is an example of what a GP2, right? This is an older version of it that it can actually be run just on a desktop. But just to reinforce this idea, right? So what you see down here on the bottom, all right, this is a transformer. That's the architecture, the AI architecture associated with this particular framework, and that's the same framework that supports GPT and chat, and the application chat GPT. All right, but here what we're doing is we're trying to predict the next word. You can see down here in this sentence, the best thing about AI is its ability to, and then what's going to happen is that you're going to have essentially a vector here, right, of different words and their likelihood to show up based off the data that this architecture has in place. What is the most likely word to show up next in this sequence of words? All right, and what we're doing is we're outputting here just the top probability. We're just doing the top 20 probabilities here, and they're not in order. I probably should have done that, but what we'll see here is its ability to learn is actually the next best object. But at the end of the day, right, if you distill these down, that's the goal, right? Is for them to be able to predict essentially what this next token is going to be based off the previous set of words that it's given. And it does a really good job about this. So if we look back, like at the technologies that support it, one of the key ones, and again, there's a list here, but in 2013, all right, Word2Vec was invented, all right, which is an important part, but also it was followed up by something called the distributional hypothesis, right? And the idea behind the distributional hypothesis, and I think I have a slide to it, so I'll talk a little bit more to that, is that words that are close together have similar meaning, and they can be predicted based off the various distance, the likelihood that they far apart they are in large corpui of text. So this is important, right? So we realize that, okay, we don't have to actually create, fairly structured models to be able to interpret grammar. We can just use essentially the location of the words as a vehicle for predicting how good it will fit in the next sentence, right? So this distributional hypothesis was key to kind of creating these large language models. And as we look through these sequence of things, again, I just want to highlight a few of these, all right? Not to talk through them ad nauseum. In 2014, attention was created as basically another hyperparameter associated with large language models. And attention is essentially, you can think of it as the emphasis on any one word, the importance of any one word in a sentence, all right? And so if you can assign attention, so there's different examples of this. So if we would say, the cat is black, all right? So in that particular sentence, right, the word black is very important for cat, right? But if we were to say, as an example, there's both a black cat and a white cat, it might be that the distribution associated with those two words, white and black, are equal as compared to more attention that was given on the first sentence. That might be a bad example, but the idea of it is essentially how important is any one word to understanding the entire string of words in which it's embedded, all right? And so transformers were also invented in 2017, all right, which is a new architecture associated with essentially, it was designed to translate language, but much of that architecture, actually the majority of that architecture, is what's used under the hood for large language models currently in terms of the generating, in terms of their applications, particularly in GPT, right? So that's used there. So it's the kind of the AI architecture driving a lot of these large language models. And what we found, right, is that instead of including a lot of the other parameters associated with how these models are trained, is that attention ends up being kind of the key component, right? So these transformers helped us move away from recurring neural networks as a baseline architecture for generative large language models. And then attention, which was created in 2014, ended up being the key component in order for them to really perform at a high level. So it's really these combinations of things, this attention mechanism, all right? And then also this new architecture associated with transformers that allowed us to kind of move forward in this GPT world. And we can see right after this in 2018, GPT is pre-trained with a transformer model, all right? And then BERT and Google, suddenly they're announcing too, they're moving off of recurring neural networks and using this transformer model with that attention component. And then it just kind of skyrockets from there. And so GPT-2 is the one that I showed kind of in the snapshot there about the way it's predicting just with the probabilities. But a lot of these components put themselves in place, right? In combination, I talked about this, so I think I'll skip over this. All right. In combination with these features, right, in the timeline that we talked about here, right? So what we saw, and that's what the question mark is there, really that's the transformer and attention architectures. So we had, again, not to review it all, but we had all of these components that kind of came together at this like perfect moment, right? Where they saw like really these increases in AI. And then we had the correct architecture that was able to take advantage of all this previous work. And that's why we saw this just massive increase in the use and proliferation of AI. We had this kind of generative AI revolution that we're in for the last 2 years. It's kind of the combination of all this kind of slow burn, and then suddenly right there, kind of right in 2017 and 18 is when things just went through the roof. All right. So let's talk a little bit more about how these models work. And I think it's important to just contextualize that there's one other component of the large language models that's really important. I think I put it here. So there's kind of these three key enhancements, right? So we talked about attention, and then there's position. That's basically the position of the words. That's kind of the word to vec concept. And there's also this thing called temperature. All right. So if you understand these three things about these transformer models, these large language models, all right, then you kind of have a general high level idea about how they're working. All right. So attention is an important one. And so what attention tells us is essentially what order that we're going to select the next probabilistic word to choose. Right? And that's kind of a word salad there. But the idea is that it might not always be best to pick the next word with the highest probability. Is that you might have to adjust, and this is what the temperature does. Essentially adjusts, at random, how random we want that next word to be, as compared to just picking the top probability, which in this example would be learn. All right. So this is an example. So we let this run a little bit more, right? So here we're just continuing to build out this large language model. You can see we're adding, new words step by step, learn from experience. It's not just a matter of, all right. So we're basically just letting this run to add another 10 words to it. But what we find is that if we don't adjust the temperature, this is the result we get. All right. So this is an example from Stephen Wolfram. All right. So he went through this experiment and showed this online. And the idea here is that if the temperature is set to 0, that means that it takes the top probabilistic word that is predicted every time. What happens is you get this. You start to see essentially just a repetition. All right. It just starts to repeat in a cycle because the next likely word is going to be based off what was done before. And if there's no variability, it's just going to start to repeat. So we see that here. This is a temperature of 0. All right. But if we increase, this is a temperature of 0.8. You can go from 0 to 1 in most of these models. What we see is a much more elegant sentence. All right. So here, what it's doing is it's randomly selecting, all right, from that list of possible words, not choosing the top possible word. And that's what generates this type of much more kind of elegant sentence. And this was an advancement that allowed for large language models to really produce high quality text in combination with the new transformer architecture. And then also a lot of the advancements that we've talked about relative to hardware, software, and just other modeling approaches. But this was a key one too. All right. All right. So some of the problems with this, all right, is that if you inherently increase the temperature, and this may be kind of obvious, but if you increase that temperature parameter, all right, what you're doing essentially is selecting, but it is from a high density of predictions. But what you're doing is you are selecting at random what the next best word might be. All right. And so what happens is that if for some reason that random selection of a word, right, isn't exactly perfect, right, it can result in what has been commonly referred to as hallucinations, right? Is that essentially what happens because these things are autoregressive, which means that it's heavily dependent on the accuracy of the previous prediction, is that once it starts to go off the rails, it goes off the rails really quickly. And that can sometimes result in what we've been seeing in terms of these hallucinations, right? Just because the nature of them is that they're autoregressive, right? So they're using the previous predictions to do the ones in the future. And if those are slightly outside of the distribution of the data that the model has access to, then it's going to go off the rails pretty quick. Kind of as we see as our comic over here, right? They just don't know how deep the water is. I think it's a good way to think about, we just don't know how close we are to those errors suddenly going off the side of a cliff, right? All right. And so this is an example here. It's kind of a clunky graphic, but I do think like over time, what's happened, right, is that the models have gradually increased. All right. But you always have kind of this leakage. There's kind of this dripping down here on the bottom. And you can think of the leakage as like, how far can we push these models until we realize that we see above the surface and we're like, okay, this is, it's giving you some pretty clear hallucinations here. All right. This was seen a lot in the early days. I think when GPT-2 was out, they acted really simple logic questions. It would just get them wrong. And we've seen it, I think, continue with GPT-3, especially relative to, current events, things like that just probably aren't in its distribution of information. It stopped in 2021. And so what's happening is I think the models are getting better and better. It's getting deeper and deeper. So the idea here is that it's hard for us, the users, to get above that surface and really see the errors, but they're always going to kind of be there. And so over time, it might be that these models are so deep that it just never happens. But it's important to remember there's always going to be a certain amount of error kind of leaking out the bottom of these, just given the nature of how they're trained and used, which can make them, and in my experience in working with some local firms to put them into production, can make kind of difficult to use, especially if you want to have repeatable, authoritative information coming out of them, and that can be quite difficult. Okay, so keep going here. All right, and then I'll get to potential concerns. All right, I'm conscious of the time here. I think I got about another 10 minutes or so. And many of you may have seen these. I think it's important to bring it up, that there's kind of these open and lots of AI researchers and people that were generating these models signed on to some of these to have a, kind of a pause. I think this was about a year ago to say, hey, let's just wait 6 months. I mean, I don't know what 6 months would have made any different, but there are some concerns relative to the rapid development of these models. And there was just another one. This is just an excerpt from that letter talking about that we're going to achieve human competitive intelligence and a profound risk to society and humanity. I think that's true, but I think if we have a real good understanding of the limitations of these models, just like we talked about, and you start to really use them over and over again, I think like a lot of this was a bit overstated. This one maybe in particular, I think that there were some concerns. I don't know if people remember this about the potential nuclear war-like event, if AI was to continue to proliferate, and maybe they're talking about decades into the future. I'm not quite as concerned about this, but this was signed on by a lot of really famous AI researchers in the community and brought up as kind of a continuous thing to think about at a minimum. All right, and there's some misinformation at scale could be a big problem, especially with the large language models in terms of the way that they're generating text. Can be done quite easily. And we are in a period of really rapid development, and I'm gonna let this run. I don't know if I can, show you this. All right. So this is a program that's using GPT in the background, but doing kind of automated search online. So you just kind of release it to the wild. I mean, even this is a bit dated now. I think this is, kind of a 6 months ago kind of an example. But I think what we're going to see. I'll just pause this. All right. But this is just an example. This is just a simple piece of software that's using GPT in the background, but it's been trained in a way where it actually goes out on the internet and starts to learn about any particular topic. In this example, it's learning about itself, actually, and then generating summarized text based off of that. So I think what we're going to see, and this is a good use case of it, is like more and more embedding into applications, kind of without guardrails generally. I think there's been just kind of a push to include this. Maybe in spaces that make a lot of sense, but in some spaces maybe that it doesn't. And this is just the beginning, right? So I think given that the technology is out there and open, kind of the development around integrating it into kind of user-friendly applications, and then the combination of whether that's able to generate text from prompts or generate images from prompts or generate even language, right? Even spoken word from prompts, I think it's going to be another thing. So you see these integrations between audio and video and text, which is already starting to occur, which could be really exciting, but also kind of, a little bit scary as it relates to kind of, how fast these technologies are moving forward. All right. Another thing associated with this, when we think about kind of, what are we concerned about, is that we do have really kind of a push in the US for, open development. There's not a whole lot of regulations. This is the European model for people that may be familiar with it, the GDPR there. That's kind of their general data protection, architecture that's available. And we don't really necessarily have that in the US. There's some that's kind of close to it. This is California version of it, which provides for some oversight and protection of personal data. But generally, we really don't have these restrictions, which is part of the big reason that GPT was able to, and OpenAI in particular, was able to develop these models so quickly, is they had so much access to so much data basically online. There was no restrictions about what they could use. We also have a lot of competition. I think so. This chart, all right, is an example of the parameter space of large language models, kind of mostly from domestic kind of companies, but also in the Chinese and kind of other global spaces. And you can see we don't necessarily have a total market capture on this. You know, there are tons and tons of these models, large language models, that are being developed and put out into the open. All right, so I mean, that's another thing relative to the space of this and the competition, which I think it can be a really good thing to help push these models forward and kind of advance development. So if you put all these kind of accommodations in place, you know, the competition, kind of the nature of, you know, I'll just go down to this, you know, kind of the rapid development, global competition, you know, in the free market, I think what we'll see is just the development and advancement in technology and availability of data. We're just going to continue to see these models kind of grow and continue to proliferate over time because of all these things that have been put into place. Which makes it a very exciting time to think about applications and how they can be used in research, things like that. You have to be a little bit concerned, you know, that there might be some potential calamities associated with all these things being put into place. But you know, in general, I'm fairly bullish that I think that this is going to be a total net positive, and that, you know, the advancements that we're seeing in this is going to be a really dramatic increase in our efficiency and our ability to be able to produce you know, really interesting products and certainly push research aspects forward. All right. So I have some final kind of pontifications here. I will say, you know, a regulatory framework, I think, is hopeful, I guess, to people in conversations that are a little bit more savvy into the space, including researchers here at the School of Data Science that focus on policy. They believe that a European-like model could be present in the future in the US. I'm not sure exactly what that might look like, but I think it would probably be more of a watered down version. But I think that would be healthy relative to the development of these things and create some type of guardrails. You know, as an example, BARD is not available in the EU right now based off how their regulatory framework is in place. It does seem to be clear that, you know, the increased cost of keeping these models is quite high, right? That it's important to remember the latest version, GPT-4, stops relative to its data set in 2021, all right? And by some estimations, you know, to train one version of this is something like the energy used for mid-sized city for an entire year. Where GPT-4 costs close to $100 million to train. All right, so explainability ends up being kind of a big issue relative to this. When I showed that kind of in that chart at the very beginning to contextualize what we're talking about, as you move further and further down kind of into the deep architectures, being able to understand exactly how they're working can be quite complicated. Doesn't mean that they don't work really well and that there aren't some ways. And I think actually explainable AI is moving on pretty rapidly. And I think actually that's going to be a nice area to think about in terms of expansion for research areas. It almost is like a pushback, I think, to the development of some of this kind of generative AI. Is that maybe the explainable AI space might actually become pretty popular for some people to generate models that work just as well, that are a bit better understood. So, you know, I think approaches for fine-tuning AI models and collaborations with, you know, with clients or researchers is likely to be more common. You know, in my working with companies here, and then also, you know, just in talking with people that are working to deploy these, it seems that's ends up being the majority of the time, you know, because you have kind of these pre-trained models already and you can pick them up and use them, but then fine-tuning them on the back end for your particular use case, you know, kind of a reinforced learning approach ends up being the majority of the work. And I think that's good. And I think it also, at some places, you know, need to create a, you know, a framework for at what point does it not make sense to continue to try and do that, right? And maybe use another approach that doesn't require so much fine tuning. And I think that that's a space where people are going to start to make choices about whether they want to use generative AI or maybe to go back to more, I mean, I guess we could say this, you know, more traditional kind of AI approaches that don't necessarily require, you know, the generation of new new text or images or sound or voice or video or whatever that might be. So I think that's it. I went through that really kind of fast, but Jack, I think is that 15 minutes for questions? Is that kind of normally the way that we go?
That's perfect, Brian. Thank you.
Yeah.
Thank you so much for giving us this overview. I think this was really helpful for me and helping to give me a little more of the context. Certainly, it seems like in the last 18 months or so, I mean, in the last 9 months, we have seen just such an explosion with, it's like one of these things where a sequel to a movie comes out and it's like, son of Zor, returns again, right? He's like, well, what was the original Zor movie? I didn't see that one, but now there's like, I'm seeing the advertising for the sequel. It's like ChatGPT 3. I didn't know there were several others before that. And so it's like, seems like it's just arrived. So it's so sudden. And I'm wondering if that's part of one of the drivers of people's fears about this, is it just seems like it happened overnight.
Yeah, 100%. I mean, when I started to look into this, and I was trying to better understand it myself. I mean, me and you are both in schools of data science, and to a certain extent, like the explosion of this even caught us off guard. I mean, I think it did, So we spent a lot of time doing kind of like a postdoc and be like, whoa, how did this happen? I mean, part of it was just relative to the ease of use of Chat GPT in particular. Just made it very accessible. And so even these methods, they were kind of in place in-house in these big tech firms. When that became online and the user interface became so simple, then people just that was a big reason for it. But also, I think when we started to look back at like how the slow burn kind of, and maybe not even slow, right, but kind of the rapid development of technologies and software and data expansion in the last like 7 to 8 years, it was almost like manifest destiny. That as soon as the mathematical approaches, the AI architecture became available, it just took off because everything else was in place.
Yeah.
And that just made it, it made essentially the foundation for kind of sharpening the pointy end of that spear possible. Because before, maybe it's a bad analogy, but the spear just didn't really exist. And then all of a sudden it was there, and it allowed it to really explode. Yeah.
It's interesting how these perfect storms of things kind of can happen, right? It's only when you had the confluence of all of these different technologies, just all were, there at the same time, that they got put together. And then there's just this explosion of innovation in this area. It's fascinating.
Yeah. And the other really interesting thing, people don't talk about it enough, is that how the big tech firms, especially for the attention vehicle, open source those innovations. And that allowed OpenAI, the company at that time, to take the innovations that were generated in Google and create GPT. I mean, so if that hadn't been like an open, research process, they never would have been able to leverage that technology to accomplish it. And now they have a multi-billion-dollar company as a result of it, which is also really interesting. Yeah.
And it's interesting, you were talking about what the cost is to train these models, and, that it takes the power of a small nation to be able to do, as probably a lot of money as well. But you still have these phenomenon like, the models hallucinating. And one of our comments from one of our viewers is asking, like, how do you tell the difference between a model that just wasn't trained on something and just doesn't happen to know versus it's hallucinating? How do you tell the difference? Or do you?
It's a good question. Essentially, it's the same thing. So what we find is that hallucinations occur in particular when prompts are given to the large language models, when the answers are outside of a density of distribution of information that has available. So like, as an example, like if we know that, GPT-4 was trained on information prior to 2021, it knows a lot about presidents. It can tell you a ton about presidential procedure, like the history of like what the presidential power. It could do a lot about that, but it can't really tell you a lot about how Biden implements his version of his presidential powers, right? Because it doesn't have a lot of density of information on him in particular.
Right.
So that's kind of what we see, is that those hallucinations have a tendency to occur because there's not enough information in the distribution of data that it has available to it. And that's why you see a lot of energy going into fine tuning, and it's almost like it's almost like whack-a-mole, like you push these models and push them, and then all of a sudden there's another set of information that it just doesn't know enough about it to accurately generate text around that. So you have to kind of put a band-aid on it and say, all right, well, let's eliminate this from the range of things that it could ask. And that's when you get the prompt and say, hey, I'm not too sure on this. You may want to think about asking it another way. And so that's sort of kind of that, how you fine tune the end of those models to make sure that don't have an expansive kind of perimeter set, that kind of control the span of the things that they have expertise on and don't. But when you're talking about, training it on the entire internet, it's almost impossible to do that,
Right.
to say, hey, these are things that it can know and not know. So the hallucination effect is essentially infinite, because you can't go in and correct every possible error that might occur. Yeah.
And another thing which is kind of interesting is you might think, okay, how could it, keep up with its knowledge base, right? So you might imagine that it would pick a number of, New York Times or CNN or whatever your favorite news source is, and ingest that information and use it in training its models. But then, of course, the Chat GPT and other technologies like this are generating the content, where you might expect that they would in the future, generating that same content. You almost get this sense of like a snake eating its own tail in terms of its training. At some point, a human being in the loop is probably important somehow. How do we keep a rein on that? Is that even a sensible question?
No, it makes a lot of sense, and it harkens back to kind of a first mover in this, ethics of data science field, which Kathy O'Neill was affiliated here at UVA, and she put out this book called Weapons of Math Destruction, and one of the 4 key components associated with an algorithm that maybe has gone awry is essentially it's eating its own dog food, right? And so it's generating information that then gets put back in to the training set and then is used for generating predictions moving forward, that it's affected the landscape of the information it receives so much that it's actually generating the information that it gets trained on. And that's like you said, like the snake eating its tail. So I think at some point, which just like any other algorithm that gets put out into the wild, regardless of how big it is, it may cost $100 million, but and you have to keep track of how often these errors are occurring. Like, how often is it hallucinating? And recently, actually, there's been a lot of interesting research, or at least, maybe, desktop research associated with the idea that GPT is actually getting dumber. Is that things that it was getting right not that long ago, it's starting to get wrong now. Yeah. And that it's starting to, essentially, it's this, entropy principle, right? Is that as the expansion of the things that it's being asked to do continues to grow, it's just getting worse and worse at it. And then at some point, you just need to stop and retrain.
Yeah, so exactly. It's almost a continuous training process, right? You can't just train it, then use it, and it's going to slowly drift out of alignment or out of calibration, right? It needs to be calibrated, but on a continuous basis in order to just keep up.
Yeah, I think it's exactly that. And then with the scale of cost associated with doing that retraining, you have to start to think that, is that model sustainable? I mean, I don't know. I mean, it might not be. And so then I think, there's been kind of a movement, especially with some of the examples I've seen, to get away from using the all-encompassing corpus of large language models that's trained on the entire internet, and then do much more specialized training, in terms of more local corpi that you can use. So it's really good at, and this is the same thing that happened with Go and chess, like all these things. They're trained on a very discrete data set, and as a result, it's quite good at that one thing, right? So I think there's been at least in conversations I've had with people that are working to develop these, there's been kind of a movement towards that.
I was struck by the thing you commented on early in your presentation about that there was one amateur chess player or something who found one little innovation that nobody had found, and he was able to then beat the learning model 19 out of 20 times or something, because the computer is just following its instruction set, right? It's following its learning model, right. But somebody goes, hey, wait a minute, if I do this, I upset it. It reminded me of the self-driving taxis, and I can't remember where it is. I think it's in is it New Orleans or something, where somebody found if they take a traffic cone, one of those orange traffic cones, and they put it on the hood of the car as a joke, it stops the car. The car does not know how to handle that, and it stops dead in its tracks, and they create traffic jams. It's like, who thought of that? That's amazing. But it means now that they have to go back, retrain their models, and say, ignore traffic cones.
Yeah, and then think about the differences between like the computer vision space that would be needed to have an automated car have enough density of information to understand and interpret every potential scenario that it could run into. I mean, that again seems infinite, and maybe that's why the realization of the dream of the driverless car just really hasn't shown up quite yet. And that example with Go. It was done by a research firm affiliated with Stanford, and it was an amateur player. And I don't know the game Go, but essentially what it did is created a perimeter around a particular move, and that if it was a human playing against a human, it would have recognized it immediately as a kind of a fairly non-sophisticated move inside the game, and counteracted it immediately. But because to your point, because the AlphaGo had never seen this, it's kind of a move you would never make in person-to-person play, because it would be so easily recognizable,
right,
that it defeated the computer because it just had never seen it before. And so it's this idea that we think about these machines as intelligent, but it's not. It doesn't learn the rules of the game. It just learns patterns of success. So if a pattern of success doesn't exist, it doesn't have any intuition about what the rules are to defeat new methods. And that's an important thing. It is intelligent in a way, but it's not intuitive about the rules or how to play the game. Only super understanding of the classical patterns for success, which is so you can put quotations around intelligence in that context, at least from my perspective. Yeah.
Brian, what's the important elements here about making and keeping innovations in the development of these models open source?
Yeah, I mean, there's a cultural community associated with that reinforces it, but I think that could be part of. I think I'll say this: we use the use case of open AI, in kind of some of our foundations courses, because it was open until it wasn't, right? Until it was evaluated as a $1 billion enterprise, and then now it's not an open source platform, right? So they went private, they started taking equity, and then they got bought by Microsoft. So I mean, it was a pretty easy transition for them, once it became clear that there were billions of dollars at stake. But I think like in other areas of our economy, so you think about the entire industry around NIH, and then how we don't deploy, new medicines. I mean, even around accounting principles, about what's required in order for us to be, financial advisors, things like that. I mean, these might be extremes, but you really don't have any of that relative to developing algorithms and putting them out in the world, or data regulatory oversight. That seems like there should be. So I think to a certain extent, in order for this to be an open conversation, for it to continue to be, known, is that it's going to require some type of governmental intervention, because the dollars we're talking about here are just too big for, even companies that have idealistic origination like OpenAI did, to not suddenly go private once it becomes obvious that that's the best way for them to go. And so I don't know if I have a great answer for that, but I think to me there should be some regulatory kind of function that allows some oversight about how these are being trained, how they're being deployed, and then exactly what methodologies they're using in order to be able to keep an informed populace about how they're being used. I think that would be a healthy step. Yeah.
Brian, thank you so much for sharing today and providing a context for generative AI. Especially as we go down this road of building partnerships between folks who are developing generative AI methodologies and the biomedical and clinical research training that is soon to be following, utilizing these methods. Thank you so much for kicking us off. And I want to Thanks everybody who joined us out in the world. And please watch next week when we have our next edition of our biomedical data science seminar series. So thanks so much again, Brian.